So we consider the stars to be black body. What is the meaning of a black body? A black body, a perfect absorber or a perfect emitter is considered or said to be a black body. So a body which emit out all the radiations which fall on it, we call that as a black body. And black body emitting out, because all the radiation it can emit out, so black bodies are emitting out radiation in all the wavelengths. Same thing for a star. We say star because it is emitting out all the radiation. It is emitting out shorter wavelength, it is emitting out longer wavelength, or a moderate wavelength. So we say star to be a black body. And how much energy emitted out by the star every second, energy per unit time, that is known as the power. And in terms of for the star, this power is also known as luminosity. So power of the star, like energy every second emitted out by the star, is refers to luminosity of the star. So the first law which explain a relation between the size of the star and the temperature of the star with a luminosity is a Stefan-Boltzmann law. What is a Stefan-Boltzmann law? It states that the luminosity or the energy emitted out by the star every second is proportional to the size of the star. Example, we have two stars, one is large in size, another one is small in size. So which star will have the high luminosity when we compare the luminosities of the two stars? The star which is having a large size will emit out more energy every second, so high luminosity, whereas a star which is small in size, if they have the same temperature, like if two stars have the same temperature but different size, so the one which is larger in size will emit out more energy every second, or it will have a higher luminosity. So we can say luminosity is proportional to size of the star. And how to get the size of the star, or we can say area of the star basically. So luminosity proportional to area of the star, and how to get the area of the star? Area is equals to 4 pi r square. The second thing, according to Stefan-Boltzmann law, it states, like example, if we have two stars of same size but different temperature. So example, if this is 2000 Kelvin example, and this one is 4000 Kelvin. Two stars have the same size but different temperatures. So the one which is having a high temperature will have a high luminosity. And luminosity is proportional to fourth power of the temperature. So this is 2000, this is 4000. So when we compare the temperature, this temperature is double, like temperature of star B is double as compared to temperature of star A. So if the luminosity of this star is L, the luminosity of this star, because the temperature is double. So if the temperature is double, the luminosity will increase by fourth power of the temperature, like the factor. So T, as it is double, so it will become, if this is L, so 2 raised to power 4, so it will become 16 times L. The luminosity will be, so luminosity of this star will be 16 times, or star B will be 16 times as compared to star A. So when we combine the two factors, we say luminosity of a star, according to Stefan-Boltzmann, luminosity of the star is proportional to area of the star, and luminosity of a star is proportional to temperature raised to power 4. So we can say luminosity, when we combine these two, luminosity is proportional to A into T raised to power 4. And whenever we replace the proportionality sign, we replace with equal to and constant. So sigma here is a constant, and to substitute area is 4 pi r square, then sigma T raised to power 4, which is used to find, if we want, if we know the luminosity of a star and temperature, we can find the size of the star. If we know the size of the star and the luminosity, we can find temperature of the star. And if we know the size of the star and temperature, we can predict the luminosity of the star. So Stefan-Boltzmann law actually relate the luminosity, the size and the temperature of the star. Then if we want to find the distance of the star or distance of the object from the source, so we can use this formula of a radiation flux. What is the meaning of a radiation flux or radiation intensity? It means how much energy is coming on unit area in 1 second. So radiation flux is equals to how much energy is coming on unit area in 1 second. So example, say we have a source is there and we are standing at position A, which is at a distance from the source, example D. So what is the flux? Flux means how much energy is coming on unit area. So there will be lot of points which are at the same distance D from this. So when we join those points, what it will make? It will make a sphere. So radiation flux or intensity is energy coming on unit area every second, and energy divided by time, that is equals to power, and this power is known as the luminosity here. So we can say the flux is equals to power divided by area, or we can say luminosity, because for star divided by area. But this area is not the area of the star. This is the flux on a unit area. Like the total area, how much flux is there, that is this area, not the area of the star. So how to work out that area? Because it will make a perfect sphere, so again area will be 4 pi r square. So we can say flux is equals to luminosity, the power of the star, divided by 4 pi r square, or we can say d square, where d is actually a distance between the star and the object which is observing the star. So if we want to find the distance, like how we can predict or how we can say the distance between the star and the earth, different stars, so we can use this technique that after identifying the luminosity, like if we work out the luminosity, flux, how much energy is coming on unit area and every second, if we calculated the flux, so we can work out the distance between the star and the earth. So how we use this formula, like this is a star and here's our earth, we are observing any star, this is star. So the distance between the star and the earth, that is given by d. So how much energy we receive on unit area in 1 second, that is called flux. And flux is always calculated on area, it's not calculated at point. Like I cannot say the flux at this point is having a value. Flux is actually calculated over an area. So if this point is at a distance d, so there will be lot of points which are at a distance d from this. So when we join all the points, so what it will make? It will make a sphere. So when it will make a sphere, so we can use a formula for the sphere, the area. Now the flux as it is calculated for area, so it will be equal to 4 pi r square, where r is the distance between the star and the earth, so we can say 4 pi d square. So area is equals to 4 pi d square. Luminosity, the power energy emitted out every second, that is the luminosity. So we can work out the flux, or using this formula we can work out the distance between the star and the earth. And how the flux vary? The flux is inversely proportional to 1 over d square. It means if the distance is double, the flux will decrease by 4. If a distance is triple, the flux will decrease by 9. If distance is divided by 5, the flux will divide by 25. So it follows inverse square law. So this technique, this radiation flux formula is used to find the distance, mainly the distance between the star and the earth. And the first formula normally used to find the temperature or the size of the star. Then standard candles. Stellar objects, we consider them as a standard candle. What is the meaning of a standard candle? Standard candle means an object or a star with a known luminosity. Like if we know this luminosity of a star or luminosity of the object, we call that as a standard candle. Like example, say we have a filament bulb, and on the filament bulb it is written 40 watts. So it is written 40 watt, it means 40 joules of energy consumed every second. So we know its luminosity, we know its power. So if we know the power of the object, the luminous object, then what we say it is a standard candle. So stars, we consider them as a standard candle and use it like we know their luminosities, and using the luminosity and the flux we can work out like if we know the flux and we know the luminosity, so we can work out the distance between the star and the object. So the definition of a standard candle are astronomical object or stars with a known luminosity. So examples of the standard candle are like supernova or Cepheid variable, like different types of stars. So Cepheid variable, they are considered to be standard candle. So the Wien's displacement law, what is the Wien displacement law? It is actually a relation between the flux, or you can also say luminosity, and the wavelength. So what happens if we are observing any star? So when we are observing any star, for example, we are observing the sun. So sun is emitting out all the radiation, as we mentioned, like all the range is there. It is emitting out longer wavelength, it is emitting out shorter wavelength, or a moderate one. So when we sketch the result on the grid for the wavelength and the flux, so what we found that sun is emitting out all the radiation, but there are peak radiations, there are radiations which are coming out more than the other. Like there is a region or a part of radiation which are having a greater intensity or greater flux compared to any other part. So when we sketch this result, so we have the radiation, like this is a sketch, the graph for different stars at different temperatures, like one is 3000, another one is 4000, another one is 5000. So star is emitting out all the radiation. Some are longer wavelengths are there, shorter wavelengths are also there, but majority of them, the peak radiation shows the majority are emitted out in this wavelength. So if we increase the temperature of the star, what happened to the shape of this graph? The peak, because if we increase the temperature, energy will increase. We have the formula E is equals to Hc over lambda. So increasing a temperature will increase the energy coming on unit area, and energy increases. So what happened to the wavelength? The wavelength will be shorter. So those stars which are having a high temperature, they are giving out mostly short wavelength radiation as compared to the stars which are having a low temperature. So around 3000 Kelvin, energy emit out is less and shorter wavelengths are more. Sorry, longer wavelengths are more. But when we increase the temperature, so what happened? The shorter wavelengths or more energy will be emitted out. So the amount of the shorter wavelength also increases. And according to this according to this Wien's law, that whenever we take a lambda max does not mean maximum wavelength. Lambda max means it is the intensity or a flux for which the wavelength is maximum. That's called lambda max. So according to Wien's law, whenever lambda max, the maximum wavelength, basically the wavelength at which the flux is maximum, that's called lambda max. So whenever lambda max multiplied by t, will always get a same result, 2.898 into 10 to the power minus 3. So using this Wien's law, we can work out the temperature of the star. How we work out temperature of star? For example, we focus on one of the star and we obtain this result. Say the blue line, say the blue part is representing the results which we obtained from the experimental data. So after obtaining this result, this will be the peak wavelength, the maximum flux. So using a maximum flux, we'll find the wavelength that is called lambda max. And this lambda max multiplied by, because lambda max multiplied by temperature is always equal to 2.89 exponent minus 3. So if we know the lambda max and this is fixed, so we can find the temperature of the star. And then after knowing the temperature of the star, the luminosity, so we can use the formula to find the size of the star, that luminosity is equal to sigma 4 pi r square t raised to power 4. So if we know the luminosity, we know the temperature from this Wien's law, so we can find the size of the star. And after knowing the size, we have luminosity, the flux is equals to luminosity divided by 4 pi d square. So we have the luminosity and we have the flux here is given. Luminosity we already know because it's a standard candle, like known luminosity. So we can find the distance of the star. So these laws are related to each other. Then the stars can be classified into different categories. Like example, because the stars, there are many things which affect. Like example, the luminosity of the star is affected by the size of the star, the temperature of the star, and the distance from us. Like maybe some stars which are appear to be having a low luminosity or low flux basically. So what happened, they might be far away from us. So this is a Hertzsprung-Russell diagram which explains different types of the stars. On y-axis we have the luminosity, on x-axis we have temperature, but you can see the temperature is in a decreasing order. 24,000, then 12,000, then 6,000 and 3,000. So the simple concept is that the luminosity and temperature are directly proportional. T raised to power 4. Like luminosity is direct proportional to T raised to power 4. So it means if the temperature of the star increases, its luminosity will also increase. If temperature of the star decreases, the luminosity will also decrease. So there are stars which are following this sequence. So those stars which are following this sequence, we call them as main sequence stars. They're following the sequence, majority of them, so we call main sequence stars. Then there are exceptions as well, which are not obeying or following the sequence, such as red giant or red supergiant. What are red giants or red supergiants? Actually, red giant, you can clearly see the red giants having a low temperature as they are on the right hand side. So they have low temperature. But they are so if their temperature is low, so they will have a low luminosity. But their size, they have a low temperature, but they have a large size, and luminosity is proportional to size or area of the star. So for red giants, temperature is low, so luminosity will be low. But size is big, that's why the luminosity increases, and increase in size is much more as compared to decrease in temperature, even though they have a low temperature, but they don't follow the sequence. They're out of the sequence as because their size is big. Then there are few white dwarfs are there. What are white dwarfs? You can see according to the scale, they will have a high temperature, but their luminosity is low. Why the luminosity is low? Because they are very small. So white dwarfs are also not following a sequence. Why they are not following the sequence? Because their temperature is low. If the temperature decreases, the luminosity will decrease. And the size, their temperature is high. So if the temperature decreases, luminosity decreases, temperature increase, luminosity increase. So if temperature is increasing, they have high temperature, so high luminosity should be there. But because the size is so small, that's why the luminosity is very small. So low luminosity by white dwarfs. And then we have a blue giants. What are blue giants? They have high temperature and they have high or they have a large size. So high temperature and large size are known as blue giants. Most of the stars are following this sequence. We call them as a main sequence, but some are not following, such as red giant, blue giants, and white dwarfs. Like as the why the because if it was following a sequence, then what should be the if all were blue giants were following the sequence, then it should be in a straight line. But you can see they're not in a straight line, they're out of this range, not following the sequence. So blue giant, not following the sequence, red giant, and not following the sequence, white dwarfs. So using the Hertzsprung-Russell diagram, we can identify, we can have a data for different stars and we can compare whether it is a red giant, a blue giant, or a white dwarf. So stellar evolution means how the star evolve in their cycle. So we can have different types of stars. We can have a low mass star. Low mass star means like same like a mass of a sun. What is the current sun? We can say these are the low mass star. And high mass star, a star can be a high mass star. It means like it will have 4 times, 5 times, or 3 to 4 times mass of the sun. So how the star evolve? So star formation, the star basically, it started with the interstellar clouds, which consists mainly hydrogen is there, helium is there, dust is there. So due to the gravitational force, the cloud contracted very slowly and they get dense enough to form a protostar. So the first stage, what happened? The dense, like the interstellar clouds, because of the gravity, slowly they come closer to each other. As a result, when these clouds come closer to each other, what will happen? It will form a protostar. Then what happened? Eventually, the concentration of the atom increases, like more atoms are there in a unit space or unit volume. So as the concentration of the atom increases, the temperature also increases at the center of the protostar. So the center of the protostar, more particles are there as compared to around it. So they start a fusion. Fusion means when the lighter nuclei join to form a heavy, so hydrogen fusion started. And that release the energy. So this is releasing the energy. But that energy is not able to expand or increase the size of the star because the gravitational force is there and this energy which is released prevent the gravitational collapse. Otherwise, if there was no energy released, then what will happen? There will be a gravitational collapse when the protostar is forming. The gravity is increasing. So as a result, the gravity is increasing. The particles will come closer to each other, and they will might reach a singularity like one point. So that is called a gravitational collapse. So because when the particles are coming closer to each other, a nuclear fusion started. So two things happen. One is the gravitational pull, which is trying to keep the star, like trying to keep the matter intact. Another one is the radiation pressure, which is outward. So radiation pressure balances with a gravitational attraction or a gravitational pull, and this maintain the size of the star, and that is how the star reaches the main sequence. So the first, we have a protostar. The protostar turn into a main sequence, like example here, main sequence, like sun-like star, they will reach main sequence. Then what happened after the main sequence? So when the hydrogen fuel ceases, the outward pressure fall, like because there is a limit for hydrogen atom present. So as the number of the hydrogen atoms decreases, so the rate of fusion of hydrogen decreases, so outward pressure decreases. Because there is an outward pressure, the radiation pressure is outward for the star, and the gravitational pressure, gravitational force is inward. So there is a balance when the star is in a main sequence, like our sun, which is also a main sequence star. So the sun is actually having a balance between the radiation pressure and the gravitational force. But once the hydrogen fusion ceases, so the star, because now it is not creating enough energy, so stars start to contract. The size of the star start to decrease. So as the size of the star start to decrease, now again the particle come closer to each other and the star get heat up. As a result, when the star get heat up, it will start fusion for the heavy nucleus such as helium. So when it will start a fusion, and helium fusion releases more energy, so as a result what happened, the size of the star will increase, because it now helium fusion release more energy, so radiation pressure is more than the gravitational force. That's why the size of the star increases and it turn out to be a red giant. So first we have a main sequence star, which is our sun right now. And then what happened to our sun? The hydrogen fusion decreases, so it start to, the gravitational force is stronger and the radiation pressure is weaker, so it start to collapse. When the particle come closer, now the heavy nuclei join to form, like compared to hydrogen, heavy nucleus such as helium, now fusion started, and helium fusion release energy. As a result, when it release energy, the size of the star increases and it will turn in the region of red giant or red supergiant. And after turning into a red giant, what happened? So when the helium fusion ceased, the outward pressure is no longer balanced with the inward. And that will have what will happen, the temperature of the star during a contraction won't rise enough to cause a further fusion. So first what happened? Star started with the interstellar clouds. They're coming closer to each other, so gravitational force is there. When they are coming closer to each other, enough reaches a certain temperature, so hydrogen fusion started. As a result, when the hydrogen fusion started, the star is emitting out energy. There is an outward pressure because of the radiation, and there is an inward pressure because of the gravity. That is balanced. We have a main sequence star. Once the hydrogen fusion used up, so the star size start to decrease because the radiation pressure is weaker, smaller, or reduced. So star size start to decrease as the radiation pressure is less and the gravitational force is more. But as a result, when it will come closer, it will heat up the star because the potential energy changes to kinetic energy, so it will heat up the star. When it heat up the star will start the helium fusion. Radiation are emitted out, but radiation pressure is low. That's why the star collapse. But not collapse to singularity here. It is like reducing in size. Then what happened? The helium fusion started. As a result of the helium fusion, the size of the star increases and it turned out to be a red giant. So red giant, because a large pressure, radiation pressure and smaller gravitational force, so it turned out to be a red giant. But once in a red giant there is a helium fusion. Then once helium fusion ceases, then what happened? Now radiation pressure start to decrease. Again the star will collapse, like the particle come closer to each other. But this time what happened? It cannot have further fusion again. And after certain contraction, like a star contracted to certain point, because of the gravity the star is contracting. So after certain contraction, the outer layer of a star become unstable and it is emitted out, goes out, the outer layer. And as a result, eject into a space as a planetary nebula, or the core of the star remain as a white dwarf. So the remaining, like the surrounding, emitted out as a planetary nebula, and this part will become a white dwarf. So this is how the star follow the sequence if it is a low mass star. So for a low mass star, what is the sequence? It started with the sun, like basically protostar. After protostar we have sun. From sun it turned into red giant, and from red giant it turned to white dwarf. So as you can see, the diagram shows how this is what will happen to our sun. That sun right now, the main sequence star, then it will turn into a red giant. So when the sun will turn to red giant, the size of the sun will increase. And then from red giant, it will turn into a white dwarf. So white dwarf is actually, temperature will be high, but the size is so small. That's why its luminosity is very low. This is what happened for a low mass star like sun-like stars. But we can have a massive stars as well, which are having a mass like 3 times or 4 times the mass of the sun. So massive stars, they have lot of fuel, but they use up hydrogen at a greater rate because they have high temperature. So the rate of fusion of hydrogen is much higher. So they have a short lifespan than a low mass star. Like a massive star cannot remain in a main sequence for a longer time because they are consuming the hydrogen at a faster rate. Main sequence stars are consuming a hydrogen at a slower, like low mass star consuming a hydrogen at a slower rate, so they can remain on the main sequence for a longer period. But for a massive star, their rate of the fusion of hydrogen is much higher. That's why they have a short lifespan in the main sequence, and they turn either into a red giant or a blue giant. So what happened? So unlike low mass star, the massive star cannot continue the fusion until it is mostly iron. And then what happened? After they are not able to undergo any fusion, it stopped producing the energy and they start to collapse. As a result, when it's incredible collapse, it produce an explosion. This explosion is called type 2 supernova. And the light from a supernova can outshine the entire galaxy. So the supernova, when it happened, the entire galaxy, the light which is coming out from that galaxy can be outshined by the supernova. And after a high mass star exploded, the entire star may have completely shattered if there are remains in the central core, like sterile material, this will be either a neutron star or a black hole. If a star is having enough mass, so either it will turn out to be a neutron star or it will be a black hole. So neither of those are easy to detect. Because why they are not easy to detect? Because they emit little or no light. Like black holes, you don't see in a Hertzsprung-Russell diagram we label black hole. Why we are not labeling black hole? Because they don't have any luminosity or they are not emitting out any light. Same thing for a neutron star, no light. That's why we are not able to sketch the position of a black hole or the neutron star on the Hertzsprung-Russell diagram. And a neutron star consists almost entirely neutron or neutrinos which are densely packed in a diameter of about 10 kilometer, and the mass can be about 3 times the mass of the sun, and the black holes are even smaller and more massive, and their gravitational pull is so strong that they can even attract or even the light is not able to escape. So this Hertzsprung-Russell diagram is not having, like, because we cannot represent the black holes or the neutron star on this Hertzsprung-Russell diagram. So the cycle of the massive star is not shown here. We can only show only the cycle for the low mass star. Is it clear?